Virtual model development of a stepper motor. Stepper motor is an asynchronous machine, the stator of which contains a control winding. The rotor is either fitted with a permanent magnet or made up of a toothed ferromagnetic magnetic circuit. The stepper motor is an impulse-excited electric machine, the movement of which is not continuous but is done stepwise. Its main advantage consists of motor performance without the necessity of any controllers, and when the motors are not overloaded, they can work without feedback. The precise control of position or rotation at a constant speed is done simply by counting steps. According to the construction, the stepper motors are divided into three groups. Stepper motors with variable reluctance. Stepper motors with permanent magnets. Hybrid stepper motors. The hybrid stepper motor accumulates benefits both of stepper motors with variable reluctance and permanent magnets. It has a very small step and high power per unit of weight. The arrangement of the stator winding is similar to this stepper motor with variable reluctance. It differentiates by the rotor that is made from a cylinder permanent magnet with mounted rotor poles along the circumference having teeth. The number of teeth determines an angle step. Typically, the motors with 50 teeth are produced, in which one step is equal to the angle of 1.8 degrees. In the stator of the hybrid stepper motor, there are usually two windings having terminals arranged as shown in 12 ways of arranging the stator windings of a two-phase hybrid stepper motor. A. 4 wires only start and end points are led to terminals. B. 5 wires also the common middle point is led out to terminals. C. 6 wires the middle point of each phase is led out to terminals, and D. 8 wires the phases are divided into the halves and the start and end points are led to the terminals. According to the types of the windings, the stepper motors are divided into the unipolar stepper motor and the bipolar one. Similarly, the control of the stepper motors is divided into the following. Unipolar control, which is mostly used for a 4-phase stepper motor with variable reluctance or for hybrid stepper motors. Bipolar control, which is used for stepper motors with permanent magnets or for hybrid stepper motors. In this type of control, the current flows through the windings are placed opposed. In a simple drawing, the rotor is replaced by a rotating permanent magnet having the north pole, red, and the south pole, blue. By switching the stator winding phases in the opposite coils, the north and the south poles are also excited. The principle of the control consists of exciting, and magnetizing, one phase only. According to the cyclogram in A, the sequence of excitation A1B1 A2B2 ensures the rotation of the magnetic field in the positive direction. The change of the direction is done through reverse switching of the motor phases. Here the current flows through one winding only. In case of bipolar control, B, the current flows simultaneously through two opposite coils. This means the current is twice higher in comparison with the unipolar type. The bipolar control differs by the necessity of change the current direction. Cyclogram of 4-tacked control magnetizing one phase of a hybrid stepper motor. When two neighboring coils are excited simultaneously, according to the cyclogram N, the motor torque is 2 times higher. The position of the rotor will follow the vector sum of magnetic fluxes of both phases. At this type of control, the current flows through all 4 windings. This type of control is used the most often. Cyclogram of 4-tacked control of a hybrid stepper motor. Combining the previous two control algorithms leads to doubling the number of stable states, cyclogram N. Consequently, an increase of positioning accuracy is achieved, called soften up, without changing the structural adjustment. The previous commutation, 4-tacked control, was the symmetrical one, and the asymmetrical 8-tacked commutation causes doubling of the number of rotor steps. 8-tacked control of a hybrid stepper motor, A, unipolar control, B, bipolar control. Other ways of controlling hybrid stepper motors exist, but due to simplification, we do not deal with them in detail here, although the modes are also included into the virtual model. Vector control. The commutation consists in simultaneous supplying both phases by different voltages. This enables to rotate the stator magnetic field vector by a softer step. Microstepper. This is done by commutation at supplying the coils by harmonic voltages that are mutually shifted by pi/2. This causes a smooth, continuous movement of the rotor. The model of the motor consists of the electrical part, and mechanical part, described by the dynamic equation. Equivalent circuit diagram of hybrid bipolar stepper motor for phase A. LA presents the inductance, Ra is the resistance of phase A winding, and UI is the electromotive force depending on the angle of the rotor. The mathematical models of all motor subsystems together with corresponding simulation schemes are displayed in Table 3. Mathematical and simulation models of subsystems of the hybrid bipolar stepper motor. Shows the complete simulation scheme consisting of the schemes of subsystems. Simulation model of a hybrid bipolar stepper motor in Simulink. A series of experiments before developing the GUI was done in order to verify correctness of the developed motor simulation model. The hybrid bipolar stepper motor parameters used for simulation are as follows: LA equals pound equals 0.058 H, Ra equals airbay equals 30 ohms, SA equals 1.8 degrees, near equals 50, km equals 0.8 Newton meters /A, TD equals 0 Newton meters, BM equals 8.10 to 4 nms/rad, damping coefficient, load equals 0.1 Newton meters, U equals 12 V, and J equals 6.10 to 6 kilograms m2. The motor simulation schemes were completed by schemes of simplified voltage sources, enabling control of the chosen stepper motor by whether the full step, half step, reduced, or shortened, step, or microstep. Just note that the time courses in figures 18 to 22 were obtained from the graphical user interface of the hybrid bipolar stepper motor, explained in detail later, in the sublecture 4.5. The graphs display the motor torque m, the angular speed omega, and the angle of displacement theta, and there are courses of the current and supply voltage at the bottom. The angular displacement starts after the voltage is connected to phase B. The angular step displacement is 1.8 degrees, i.e., 90-50. The low torque influence on the angular displacement is very small. Time courses of the hybrid bipolar stepper motor at full step and magnetizing one phase. The step displacement in this control mode control comes to a half in comparison with the previous case 0.9 degrees. Also, the low torque has lesser influence on the angular displacement like in the previous case. Time courses at the full step and magnetizing both phases. Interchange of active coils results in a varying torque and angular velocity, as shown in the simulation results of half step. The angle displacement step is 0.9 degrees. Time courses for the chosen half step. In the vector control, two phases are supplied by different voltages. This allows the rotation of the vector of the stator magnetic field. In our case, the nominal value of the voltages U1 and the second one has the value that ensures the constant step. In this case, this is U2 equals 0.4 U1. Time courses for vector control and step equal to 0.45 degrees. At microstepper, one phase is supplied by the sine voltage and the second phase by the cosine voltage. It is possible to replace the harmonic voltage by a discrete course with a low frequency of 1.5 Hz. The achieved final step is 0.21 degrees. Time courses at the microstepper with a step 0.21 degrees. Similarly, like in the previous case, GUI application was developed for analyzing both the bipolar and unipolar hybrid stepper motors. The chosen supply mode is selected by a button. The application allows to implement a simple change of parameters to choose the mode of the motor run to load the motor and to visualize results in 4 basic charts, for the motor torque, angular speed, the angle of the rotation of the rotor and the line voltage, and the currents in the respective phases. The GUI screen displays the motor torque m, the angular speed omega, the angle of displacement theta, and there are courses of the current and supply voltage at the bottom. GUI screen for the stepper motor. The panel type of motor upper right contains 2 buttons, bipolar SM and unipolar SM, where the user selects the mode of basic control of the stepper motor. After selecting the chosen mode, the button turns green. The panels, A, for selection of the stepper motor control mode and, B, for inputting control and simulation parameters. The panel control mode A, contains 3 further subpanels. In the subpanel direction, a direction of rotation is chosen. In the subpanel step modes, a value of the step is chosen from the choice, full step, half step, reduced or shortened step for the vector control, and, the last choice, microstep. In the last subpanel power supply phase, It is possible to choose either the active one or both phases of the motor. This possibility is available only when the full step is chosen. In the panel Other Simulation Parameters B, the user inputs further information required by some modes of control. Here the first panel box is accessible only if a reduced step is chosen in the control mode panel.